All right, so let's take a look at the 2019 AP Calculus free response number two. This was an AB only question, but this is a pretty basic topic in the AP Calculus exam that the BC student should definitely also be interested in. So I would recommend that students from both classes pay careful attention to this particular problem. All right, so this is a pretty standard AP question, as I said. And you can recognize it right away because once you see this table of values, you know it's a question that they like to ask every year. And there are certain things that we can count on that are going to be included in this particular type of question. So, a brief overview, we've got a particle. It's called particle P, and we've got the velocity of it. It's moving along the x-axis, given by the differential function v sub p, where it is measured in meters per hour and t is measured in hours. So we've got selected values given in the table above, and we know that at time equals 0, particle P is located at the origin. Okay, so some things that we know right away when we see this type of problem. First and foremost, there is going to be somewhere on this question where you're required to find an average rate of change. And by that, what I'm talking about is your traditional slope that you would find in an algebra class. Y2 minus y1 over x2 minus x1, rise over run, delta y over delta x, whatever you've referred to it as. You're going to have to find that. And the reason is we don't have a function given to us. So normally in calculus, when you find a rate of change, what that means is you're going to take the derivative of a function and plug in a certain value, and that's going to give you the rate of change at a specific time. But in the absence of a function like we have here, where all we have are selected coordinates along the way, the best you can do is estimate the derivative, and the way we estimate a derivative is by using our average rate of change instead of instantaneous rate of change. So once you see this table of values, you pretty much know that that's going to be on there somewhere, usually, not always, but usually in part A. We also know that somewhere we're going to get a Riemann sum or a trapezoidal rule. It's going to happen. The question is just which one are we going to get? So again, as soon as you see this table of values, you know that's coming. And then some important things from the prompts. The word differentiable, they didn't give you that just as an aside. That's important. And when we see that the function is differentiable, that means that it is also continuous. And oftentimes what they're doing here is they're setting us up to use one of the main theorems, like intermediate value theorem, mean value theorem, because one of the requirements before you're allowed to use those theorems is that your function is differentiable and continuous. And so they're telling us that for a reason. We should pay attention to it. That's going to be a big deal. The other thing here is they've included units. So we've got meters per hour over here. We've got hours over here for t. That's a big deal. If they give you units, you should use those units. And so let's just be careful with those. Let's be sure that we use those appropriately and consistently throughout the problem. All right, so the last thing to talk about here is that on particle P at time equals 0, its position is at the origin, which means that when we're finding out displacement of particle P or total distance traveled, all that stuff, we don't need to worry about any initial position for P because it starts off at 0, so that simplifies our calculations a little bit. But that is often something that you're asked in these questions as well. So jumping in then, part A, justify, and here we go, so right away we have the theorem, why there must be at least one time for 0.3 to 2.8 at which v sub p prime of t, the acceleration of p, equals 0. So they're essentially saying there's got to be some place on this interval where the derivative is 0. Prove that. Now, we're going to pull this table up here so we can actually see the values. The first thing to notice is that they were very specific about the interval. The problem itself goes from 0 to 4, but they narrowed that down for us from 0.3 to 2.8. And again, they're doing that intentionally. On the AP test, when they give you information, they're trying to be helpful. And in this case, this information is very helpful. Because what we can do then is just look at those two coordinates and notice the average rate of change between those two coordinates, if you subtract correctly, would be 55 minus 55 over 2.8 minus 0.3, which is 0. And so that's a really big deal, and you're going to have to show this work. Anytime on one of these problems that you find the average rate of change, be sure you show this work right here. This is called the difference quotient. If you don't show this subtraction, you could lose points on this type of question. So you always want to show that work. Even if it's easy to do in your head, which this clearly is, still show this so that the AP readers know that you understand where that 0 is coming from. And so we show that the average rate of change is 0. And the theorem here that we're going to be working with then is the mean value theorem, which essentially says that if the average rate of change over the interval is 0, then there's got to be somewhere in between those two coordinates where the instantaneous rate of change is also 0. So here's how that should look in your response. And let's break this down into two parts. Part number 1 is basically your justification that the theorem can be used in this situation. And that justification is that since the function is continuous on the closed interval and differentiable on the open interval, we know the mean value theorem applies. So we've just got to state that, first and foremost, that the function is in fact continuous here and differentiable here. You don't need to prove that that's true. They've told you in the prompt that it's differentiable, and as long as it's differentiable, we know it's continuous. You don't need to say anything about that. We just need to state that these things are true, and therefore we know that the mean value theorem applies. Notice a tiny detail here is that the continuity has to be on a closed interval, and the differentiability is only on an open interval. I'm not going to go into detail about why that is. That would be a whole other video. But just recognize that tiny detail is that it needs to be continuous on the closed interval and differentiable on the open interval. Then we can say that since the average rate of change of this function on this interval is equal to 0, we've shown that up here already, so we don't need to talk about why that is. We've already demonstrated it. The mean value theorem guarantees that there must be some t value on this interval such that the instantaneous rate of change also equals 0. Notice that I'm always using specific function names. I didn't say since the average rate of change of the function, because if you're generic like that, the grader doesn't know which function you're referring to. Are you talking about the v sub p of t, or are you talking about v sub p prime of t? There are two different functions in this problem. So instead of just generically saying the rate of change of the function, I'm being very specific about which function I'm talking about. And so again, all we're saying here is that the average rate of change is equal to 0, which is what this bit of the sentence is saying right here. And therefore, the MVT, which is short for mean value theorem, guarantees that there must be some t value in between here, such that v sub p prime of t also equals 0. And that's it. We've used the theorem appropriately here. We've shown that this is true. You don't actually have to name the mean value theorem, but it helps a lot. So I would recommend that you do that. And that's all we've got here on part B, or A, excuse me. All right, part B. We knew this was coming. The only question was whether or not it was going to be rectangles or trapezoids. And in this case, it's a trapezoidal sum. And they want us to approximate this integral. Now remember again, we can't find this integral directly because we don't actually know what this function is. So the best thing we can do is approximate it using the areas of either rectangles or trapezoids. And in this case it's trapezoids. And there's not much to say here other than it's a formula. So we'll talk about it a little bit, but if you're not familiar with the trapezoidal sum formula, that's something you should definitely go back and review. But here's what the work on your paper should look like. I'm rewriting the question, the prompt that they gave me. I'm using correct notation. Please don't forget your D of t. And I'm saying that this integral is approximately equal to this work because, again, we're only approximating the integral. We aren't finding the exact value of it. And so this number here, the 0.3, that is the distance from 0 to 0.3, which we get just by subtracting. So 0.3 minus 0 equals 0.3. And then I'm multiplying, and in parentheses, I'm adding this height and this height, or this y value and this y value, or v value, whatever you want to call it. So 0 plus 55, and I'm dividing that by 2. And all this is the formula that gives you the area of a trapezoid. And it's a trapezoid that starts at 0 and goes to 0.3. Some of you may have learned to put the 1/2 out here under the 0.3, and that's fine. It doesn't make a bit of difference. Wherever that 1/2 is, it's going to do the same thing. And then our next trapezoid, has a width of 1.4, and that's because the distance from 0.3 to 1.7, you just subtract. 1.7 minus 0.3 is 1.4. And then in parentheses, you add these two numbers together and divide by 2, which is what we have here. And then 1.1, again, is just the subtraction of 2.8 minus 1.7. That gives us 1.1. We add up these two numbers and divide by 2. Enter this into your calculator and be so careful here. It's so easy to miss a parentheses, to miss a negative sign. Any little typo can make this go wrong, and as an AP grader, I can tell you we see this all the time where the work is perfect, the answer is wrong, and you can tell it's just a calculator typo. So really, 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 you need to make it an emphasis to practice your calculator skills and make sure you're comfortable entering things like this with lots of parentheses, just to be sure that you can consistently get the correct answer. But that's it. It's 40.75. There was no third decimal, so we weren't held to the third decimal rule on this problem. But that is it for part B. Okay, now on part C, they do this a lot. They've given us a second particle with an actual function, which means we no longer have to rely on estimation techniques. We can actually derive the function directly. We can integrate the function and get exact answers rather than approximate answers. We've got the same interval, 0 to 4. This particle, the velocity is determined by this function. And first and foremost, we want to find the time interval during which the velocity is at least 60 meters per hour. The at least part is important. That means 60 is included. It's not when it's greater than 60, but when it's at least 60. So that means 60 or more. And there are lots of ways to go about getting that answer with a calculator. My preference is a graph. So I opened a graph page. I typed in the function. Notice I was very careful to put multiplication symbols in between 45 and the square root, and in between the square root and the cosine function. I found that leaving those multiplication symbols out can lead to miscalculations, so just be really careful about those. I always recommend using them if you're in doubt. But there's the function, which is that blue curve there. I also graphed the function y equals 60, which we have here is stored as f of 2, and I'm just finding the intersection points. If you're not comfortable with this in the calculator, please practice it. When you graph these initially, this picture that you see here is not going to be in the default window. You're going to have to change your window settings to be sure that you see this picture clearly. Learn how to use the Analyze function feature. You will go to Menu, Analyze Function, Intersect to figure out where these intersect. You have to click to the left of this point and click to the right of this point, and then this point will appear. If you haven't changed the settings on your calculator, you're likely only going to get 1.8 or 1.86 showing up here. And we know on the AP Calculus test, we need more decimal places than that. So if you're in your graphing screen and you go to Menu Settings, there's a place where you can change the display digit option away from float 3, which is the default. And I recommend just changing that to float. And if you do that, then whenever you get a coordinate on your graphing screen, it's always going to give you enough decimal places. Now, important to note that those settings are different from the main settings of the calculator. If you're on your home screen and you go to settings and you change your display digits to float, which everyone should absolutely do, that does not impact the graphing screen. The graphing screen has its own settings. So you've got to be sure to go into the graphing screen and change the settings there as well. Always, I recommend having that on float. But anyway, all that to say that we have these two numbers now. So I know that anywhere from this t value to this t value, my function is either 60 or larger. So now I'm going to go ahead and state that. So the velocity of the particle is at least 60 meters per hour from this time to this time, hours. Notice I'm being very careful to include units on this answer. But that is the answer to the first half of part C. Now, it wants us to find the distance traveled by particle Q during this time interval. The way you find distance traveled is you integrate the absolute value of the velocity. Remember, if you just integrate velocity, it's going to give you displacement or net change, but it's not going to tell you the total distance traveled. To get that, you must integrate the absolute value of the velocity, which is what I do in the calculator here. There are lots of ways to get the absolute value symbols here. My preference is that I actually type in the letters A, B, S, parentheses, and then enter my function inside of those parentheses, and that's my preferred method. There are other ways to accomplish that. But also notice that since I have graphed this function already, the calculator automatically stored this function as f1 of x. That means when I'm in my main calculator screen, I don't have to retype that function. I can just use f1 of x, and it's going to know what function I'm referring to. So you integrate the absolute value of that. Here's your answer. Remember, we've got to represent that with 3 decimal places. Again, be careful that your notation is accurate. Don't forget your dt. But what we have here is 106.108 meters, and that should be the answer to part C. So again, notice this had 2 questions in it. One was find the time interval, so that's what we did here. Second was find the total distance traveled, which is what we did right here. Be sure you answer both of those. A lot of students sometimes will forget to directly answer the questions that are being asked. They'll show a lot of work and then never actually get around to declaring their answer. So just be really careful that we've addressed both parts of part C. All right, part D. At time equals 0, particle Q is at position x equals -90. So unlike particle P, which was at 0 at the beginning, this particle actually starts at -90 and begins moving from that spot. So then it says, using the result from part B, which I'm going to put right here, and the function v sub q from part C, approximate the distance between the particles at time equals 2.8. So when we did part B, they didn't really talk about what that integral gave you. But what the integral gave us in part B when we integrated from 0 to 2.8 was basically the change in position. And since particle P started at 0 and the change of position was a positive 40.75, we know that now at time equals 2.8, this is where particle P is located. Now, in order to find change in position for particle Q, we also need to integrate that velocity function, which is what I'm doing over here. So what this expression is doing then is saying -90 is where that particle is currently at. And then what I'm going to do is add to that however much the position of the particle changed from time equals 0 to time equals 2.8. So you start at -90, and then you add however much change there has been, and this is the end result, which means that that particle moved to the right a whole bunch. To go from -90 to 45, that means that particle had to move forward about 135 units, which is what this integral right here would tell you. If you integrate that, you would get, a positive 135 point something. And so -90, which is the starting point, plus however much it moved forward, will tell you where that particle currently is at 2.8. So we write that in our response. Of course, this is the calculator screen. This is what you would actually write on your paper. I'm being careful to use units again. And then we want to find the distance between them. So if particle Q is at 45.937 and particle P is at 40.75, you just need to subtract those to find the distance between them. Remember that distance is always positive, so if you subtracted this in the opposite order, you would just need to change the sign to positive. Technically, you would put an absolute value around this. That way, the order of subtraction wouldn't matter. You're going to get a positive answer no matter what. But the distance between them is 5.187, and so I'm going to state that here, that the distance between particles P and Q at time equals 2.8 is 5.187 meters. Now, I did get a little bit lazy here. Please forgive me for that. Technically, instead of using this rounded number, I should be using this large decimal over here. I should be saying this big decimal minus 40.75 is going to give me the correct answer. I just knew in this case that 3 decimal places was going to be enough to get me the accurate answer that I needed. But either way, we've answered all the parts of this question here. We found the total distance, or found the current position of particle Q. We already knew the current position of particle P. Subtract those 2 positions and find out that this is the distance between them at this time. All right, so that was it for number 2. I highly recommend at this point, if you feel comfortable with this question now, to go on to previous exams that ask a similar question and just to see how comfortable you are with it. Now, just like number 1, notice that they ask a question like this every year. So including 2019, we've got the past 5 years where they had a question like this every single time. And it's just small differences. Sometimes they ask for left rectangles to be used or right rectangles to be used to approximate integrals. Sometimes it's trapezoids. Sometimes it's calculator. Sometimes it's not. Remember that on non-calculator questions, you don't always have to simplify things all the way down to their final answer. So keep that in mind. That can save you some time. Although we do know this year in 2020 that it will be a calculator response. And so you can count on using your calculator this year and being able to use that to get exact answers more easily. But anyway, I hope this was helpful. Please reach out to me again if you've got any questions on this, and I'll see you soon for number 3.